Okay, hello everyone. My name is Rebecca Porter. I come from the University of St. Mary, and I'm the interdisciplinary studies student that they talked about earlier. And so today I'm going to talk to you a little bit about modeling moisture flux using equation discovery. And so if you don't know what moisture flux is, this image on the left here is a good visualization. You can sort of, it's the rate at which moisture flows through a given area. So you can sort of imagine these lines, these arrows pointing upwards as particles of moisture moving through the atmosphere. And when you get a vertical movement, that generally means that you're also going to get like these beautiful clouds that you see on the right. So yeah, anytime you have moisture moving upward in the air, you generally get cloud development and precipitation development. And that's why I want to study and improve the modeling of this variable because of the impact that moisture flux has on cloud development and precipitation. And so a little bit about traditional and new climate modeling methods that we have today. As you just saw from the presentation like 2 seconds ago, we have sort of a grid and equations within that grid that model atmospheric processes. And it's great, except for when you want to model things that are subgrid scale processes, which means that they're smaller than the original grid size. Moisture flux is one of these processes that is much smaller than the grid size. And so it is not as accurate when you take it in a larger scale. You sort of have to generalize a little too much for it to be accurate. And so to sort of overcome that issue and the computational expense from modeling these smaller subgrid scale processes, people are looking into machine learning. And that's great as well because it's a more accurate, more efficient. But the problem with machine learning is sometimes the models aren't always interpretable. You can ask the machine learning model, how'd you get that answer? And it won't be able to tell you what. Like it just knows the pattern, it doesn't know the why behind it. And so a way to overcome both of these issues is equation discovery. It's what I did my research on this summer. And it's basically a way to discover equations. This graph here on the left side is a basic example of that. It's linear regression, where you have your input and your output variables, and you're trying to map a relationship between the two. And so if there's a linear relationship, linear regression is great. But if it looks a little bit more like this thing on the right with all the waves and whatnot, it doesn't work so great. A line's not going to help you there. So I use something called symbolic regression. That's one of the methods I use. Where you input your data and it tries to map, like I said, a relationship between your input and output. And it will basically search through this space of mathematical operators like add, subtract, multiply, divide, log, all that stuff. And it creates an equation that shows the relationship between your input and output. And so the equation might look something a little bit more like, I should be pointing with this, shouldn't I? This one here, the equation tree, where at the bottom, you see, okay, well, I have an x here and an x here, and it's telling me I need to add those two x's. So now I know it's 2x. But then now it's telling me I need to add the sign, apply that sign to the 2x. So then I know that my equation is y equals sine 2x. And so that's how symbolic regression works. And I also use another method called piecewise regression, where you have something called a breakpoint. And it essentially tells us where the slope in your data changes. That's where your breakpoint is. And then it fits two different linear lines around that breakpoint. And you can have multiple breakpoints, but I only used one. And so it outputs an equation like this on the screen here. And it looks nasty, and it kind of is if you don't know what's going on here. But really what it is this part y equals ax plus c is really just a y equals mx plus b, but for your first segment here on the left. And then to account for the second segment, you have this chunk here, the plus all that stuff. And so this first term here, the beta, that just accounts for the change in slope between segment 1 and segment 2. So it's not the slope of segment 2, it's a change in slope between the two. And then this symbol here, that is going to be where the breakpoint or where the change in slope occurs. And then the h of x minus this symbol, it essentially is 0 when x is less than 0, and it is 1 when x is greater than or equal to 0. And then we also have a noise term here, because not everything's perfect. And so before I could apply any of this, I first want to talk about like the equation that I was hoping to get. I used the real world or real geography data at the low res as Sunduk mentioned. And then I just wanted to focus on where moisture would be most abundant. And so I thought that July would be a good month to look at because that's our summer month here. And then I looked specifically over near the Caribbean islands, over the ocean, because moisture is like quite obviously abundant there. And then I focused just on the lowest 3 levels in the atmosphere, so 723 meters above the surface and below, because that's where I found when I was sort of mapping out the moisture, that's where it was most abundant. And so I was hoping to find an equation kind of like this with my equation discovery, where W prime Q prime is the moisture flux, that's what we're trying to predict. And then dQ dZ, that is what we're inputting into the model. That is the vertical gradient of moisture, or how moisture changes throughout the vertical movement in the atmosphere. And then I was hoping to find this eddy diffusivity constant using equation discovery. But before I could do any of this, I had to do some background math, of course, because in the data set, there was actually no DZ in there outputted. There was no W prime Q prime, unfortunately, for my poor self. And so I had to, with the help of you, I had to figure out how I can find this data basically. So I used R for dry air, which is coming from the ideal gas law, virtual temperature, gravity, and then this is the change in the log of pressure. And then for W prime Q prime at a specific layer in the atmosphere, I use moistening tendency at that layer times the change in height of that layer. Then I added all the layers below it, plus the latent heat flux going upward into the air generally, I think. And that found my W prime Q prime. After I did all this data pre-processing, I could finally apply my modeling methods. And the first one I did was piecewise regression. And what I first want to point out is that these are all 3 different equations, one for each layer in the atmosphere. And what I noticed was that piecewise regression had a really hard time finding the break point, as I said, where that slope changes on these 2 levels. So the middle level and the lowest level closest to the atmosphere surface, or I mean the Earth's surface. It had trouble finding that breaking point, but it did well for the fairly well for the highest level. And so because it did so well on the highest level comparatively, I outputted that equation down here. And like I said, it looks nasty, but if you really break it down to its components, where you have the y equals mx plus b in the beginning and all the other stuff for the second segment to the right, it's really quite interpretable to me, at least I feel like. So then I was also able to apply symbolic regression, where I just put add, subtract, multiply, log, and inverse as the operators that I could choose from. And what I found was really interesting, that symbolic regression was really much easier able to find the shape of the data comparatively to piecewise regression. Now the R-squared values are much lower, which is unfortunate, but I did find it interesting that it could at least pick up these sort of weird little tails at the bottom here with piecewise, where or symbolic, where with piecewise all it did is just change the slope a little bit lower. And so for this, it also did better on the upmost level. Oh, there we go. Okay, yeah, I did better on the upmost level. So I took that equation, which is what you see here on the left, and then I simplified it for you guys, because I guess I'm just that nice. And that is here. And it's not much simpler, actually. So that's something that I found is actually a really difficult equation to understand. And so I wanted to point out that if I were to have changed this inverse to a square root, for example, that means the equation would also change, and that would also mean my prediction to the plot would change, the R-squared values would change. And so what I really did was I just picked the smoothest curves that looked the best. There was really no like actual scientific reasoning behind the one that I chose. Just it looked the best, it had the best R-squared version. So yeah. So summary, I applied piecewise regression and symbolic regression to model moisture flux. And what I learned is that there needs to be a bit more of a accurate and interpretable equation for this research to be worthwhile. Not like the stuff you saw on the last screen. If that was how all of them were, it maybe not be that great. And then I think I could do that by using hyperparameter tuning. So tuning how many generations it runs for. And I actually, for symbolic regression, it's a genetic programming method. So I didn't really actually get to use any of the genetic programming features because of lack of time. But then I think I could also add more features, such as temperature and pressure, maybe hopefully simplify and improve that accuracy. I think I could maybe try to add other function possibilities, and all of this with an underlying understanding that I want to improve computational efficiency. And so with that, if you have any questions, I would be happy to take them.
Due to the time limit, we'll take 2 questions maybe. Anyone from the audience?
If anyone has a question online, please raise your hand and I'll unmute you.
Marissa. Oh no, she's not. Sorry. Marissa sent you a cloud.
Yay, thank you, Marisa.
Okay, great. I guess we don't have many questions. So let's welcome our, thank you, Rebecca. And we'll welcome our second presenter, Thomas.